Hello everybody. In this session, we are going to think about transistor voltage divider biasing circuit. At the end of this session, students will be able to analyze a voltage divider biasing circuit for a transistor operating in common emitter amplifier. These are the contents of today's presentation. Now let us go for the basic circuit diagram of voltage divider biasing circuit. Now this figure shows the circuit diagram for a voltage divider biasing circuit, also called as a self bias with emitter bias. So voltage divider biasing circuit is designed using two resistors R1 and R2. The base biasing voltage is applied from a single DC power supply plus VCC using the two resistors R1 and R2 which are connected in series. So R1 and R2 are acting as a voltage divider. So some part of this VCC, so which is appearing across R2 is applied to the base of transistor with respect to ground. So that will set a desired value of base current IB and corresponding to that a desired value of collector current IC. So IC is decided by input base current IB. So in addition to this R1 R2 voltage divider that is used to forward bias a base emitter junction of transistor, considering in-paid transistor, one more resistor is connected in the emitter terminal for a biasing of base emitter junction biasing of a transistor, that is the external emitter resistor RE. So that's why this biasing circuit can be called as a voltage divider biasing or self bias with emitter bias. So using R1, R2 and RE, base emitter junction of a transistor is biased and a desired value of base current IB is set. Corresponding to that, we are having a DC collector current in the collector circuit. So now transistor is working as a common emitter amplifier in which the input AC signal that is to be amplified is applied to base of transistor. So before application of this input AC signal, the base emitter junction is forward biased and collector base junction is reverse biased using single positive DC power supply of voltage in general plus VCC. Output is taken from collector and the resistor collector resistor RC is connected in collector terminal. So that is used to limit the value of collector current as well as to produce the output voltage. So voltage between collector and emitter, that is the VC, that is the output voltage of this transistor. The effective input voltage for transistor is voltage between base and emitter, and the voltage appearing across R2 is a voltage at point B at base with respect to ground. So effective input voltage for transistor is VB is a resultant of the voltage appearing across R2 and while transistor is conducting, voltage appearing across emitter resistor RE. Now let us simplify the voltage divider biasing circuit using a Thevenin's theorem. So by applying a Thevenin's theorem to base emitter circuit of the transistor, that is for a voltage divider, we can replace VCC R1 R2 by its simplified circuit diagram using a Thevenin's theorem, a Thevenin's equivalent circuit. So this figure shows the circuit diagram for a Thevenin's equivalent circuit of voltage divider biasing circuit around a base emitter circuit. So VTH is a Thevenin's equivalent voltage. Using a Thevenin's theorem, it is a voltage appearing across resistor R2 applied at the base with respect to ground. So Thevenin's equivalent voltage VTH, so that is given by R2 upon R1 plus R2 into total voltage, that is VCC. So it is a voltage at the base of transistor with respect to ground, also designated as a VB, Thevenin's equivalent voltage. So this will decide a desired value of IB. And RTH, so RTH is Thevenin's equivalent resistance. So it is a parallel equivalent resistance of voltage divider biasing circuit R1 and R2. So it is a equivalent resistance seen from the base of a transistor looking into the voltage divider R1 R2 RTH. So using Thevenin's theorem, RTH Thevenin's equivalent resistance is equal to parallel equivalent resistance of R1 and R2. R1 and R2 are coming in parallel. So the resistance of voltage divider seen from base of transistor looking into voltage divider. So that is equal to R1 R2 upon R1 plus R2. So we can just replace the circuit around base emitter of transistor by a voltage source VTH, open circuit output voltage source VTH from R1 R2 and RTH. So the equivalent resistance is shown in series with the voltage source VTH. So let us go for the stabilization of Q point. Whether this biasing circuit, voltage divider biasing circuit, which is most commonly used in a common emitter amplifier, it is able to stabilize the DC operating point or quiescent point of a transistor while working as an amplifier. Now let us discuss the stabilization of Q point with respect to this voltage divider biasing circuit with emitter bias. As the temperature, surrounding temperature increases or junction temperature of a transistor increases, the reverse saturation current increases. As reverse saturation current increases, the total collector current increases, because collector current depends upon the current due to the input base current IB and the leakage, reverse current or leakage saturation current. So that depends upon temperature. As IC increases, I also increases, because I is given by IC plus IB. So as I increases, emitter current I increases, the voltage drop across emitter resistor RE also increases. So that is designated as VE, voltage at emitter with respect to ground across emitter resistor RE equal to I into RE. So voltage appearing across RE increases. So this reduces the value of base current IB. As voltage across RE increases, the effective voltage between base and emitter will change. Since the voltage from voltage divider R1, R2 is fixed, VTH is fixed, and VCC is fixed, and once the transistor is turned on, the voltage between base and emitter remains approximately constant. So as voltage across RE increases, the base current IB decreases. As IB decreases, because IB is given by VTH minus VB minus VE upon RTH. So as IB decreases, IB controls collector current IC. So this reduces collector current, because IC is beta times of base current IB. And thus initial increase in collector current due to rise in temperature, and that is due to increase in reverse saturation current. So that is compensated. Collector current IC comes to its initial value, original value, and thus the Q point, whose x coordinate is VCQ and y coordinate is ICQ, is stabilized. So thus voltage divider biasing with emitter bias provides stability to the DC operating point or quiescent point of a transistor in common emitter amplifier. Now let us go for the DC analysis of this biasing circuit in the common emitter amplifier to obtain values for DC operating point or quiescent point Q point like VCQ and ICQ. Let us go for first ICQ, DC collector current at Q point. So use KVL, Kirchhoff's voltage law, to base emitter circuit of second figure, the circuit diagram shown in the second figure. So going in a clockwise direction, starting from VTH, we can write the voltage equation VTH minus IB RTH, voltage drop across RTH, parallel equivalent resistance of R1 R2, minus voltage between base and emitter minus VB minus voltage appearing across emitter resistor RE equal to 0. So this can be written as VTH minus IB into RTH minus VB minus, for I, emitter current I, we can write IC plus IB, because the emitter current is sum of collector current and a base current. So IC plus IB into RE equal to 0. So VTH, further simplification, VTH minus IB RTH minus VB minus beta into IB plus IB in bracket beta IB plus IB bracket complete into RE equal to 0. So let us rewrite this voltage equation for the input base current IB. IB equal to VTH minus VB divided by RTH plus into bracket 1 minus beta into RE. So using this equation, we can calculate the value of input base current IB. IB will decide a DC collector current at a DC operating point or quiescent point, Q point. So equation for ICQ equal to beta into IB, where beta is current gain of transistor in a common emitter circuit configuration. Now let us go for equation for VCQ. VCQ, apply KVL to collector emitter output circuit of common emitter amplifier. Starting from VCC, let us go in anti-clockwise direction. VCC minus ICRC, voltage drop across collector resistor RC, minus voltage between collector and emitter, minus voltage appearing across emitter resistor RE equal to 0. So this can be written as collector to emitter voltage VC equal to VCC minus ICRC minus I into RE. So from this we can write the equation for collector to emitter voltage at a Q point, quiescent point, VCQ equal to VCC minus ICRC minus I into RE. So using equation number 1 and equation number 2, we can get the quiescent point values for a Q point values VCQ and ICQ. Now let us go for the stability factor. Stability factor for a voltage divider biasing with emitter bias. Let us get the equation for stability factor. Yes. Apply KVL to base emitter circuit of figure number 2, circuit diagram shown in the figure number 2. So VTH equal to IB into RTH plus VB plus I into RE. So this is equal to IB into RTH plus VB plus IB plus IC into RE. So let us differentiate this equation with respect to collector current IC. So as VTH, VB are constant, so 0 equal to RE plus RTH plus RE into change in base current due to change in collector current, derivative of base current with respect to collector current. So that is given by minus RE upon RTH plus RE. Let this is equation number 3. In general, stability factor for transistor in common emitter circuit configuration is given by S equal to 1 plus beta upon 1 minus beta into derivative of base current with respect to collector current. So from equation 3, let us substitute the value of derivative of IB with respect to IC. The stability factor for voltage divider biasing circuit is given by 1 plus beta into 1 plus RTH upon RE divided by 1 plus beta plus RTH upon RE. So this equation indicates that stability factor S varies between 1 for a small RTH upon for a small value of RTH upon RE and 1 plus beta for a larger value of RTH upon RE. So for better stability of Q point, for a smaller value of S, RE and VCC should be larger and RTH should be small. The student can pause video here and think over this question and try to answer this question. So what is the use of RE resistor in common emitter transistor amplifier? RE is used to stabilize the Q point. It causes a current series negative feedback. The feedback voltage appearing across RE automatically controls the value of input base current IB. So as VB and VB are constant, so IB controls IC and thereby the Q point is stabilized. So this is reference. Thank you.